Cold coffee, my favorite. All right. X-ray interactions with the patient, within the patient. There are three to get down, okay? There is the photoelectric interaction, Compton scatter, and coherent scatter. We're going to look at all three of these. The entire remnant beam that carries the image signal are controlled by the relationships of the set electrical technique variables and the atoms comprising the tissue within the patient status. What is the patient made of? Okay. By the way, what are we made of? What kind of atoms are you going to find inside a person? So water is not an atom, it's a molecule, right? But what is water made of? And hydrogen and oxygen, right? So you're roughly speaking about 75% water, right? And water is hydrogen and oxygen. One oxygen molecule, two hydrogen molecules, H2O, right? So you're largely composed of hydrogen and oxygen. And if you're any fan of sci-fi, you know that we are carbon-based life forms, right? So we're built on carbon, right? Our proteins are built on carbon. So the most common elements in our body are carbon, hydrogen, and oxygen, which are much less dense than tungsten, right? And much less dense than titanium, which you'll find in some patients who have had surgical repairs, right? Hardware put in, okay? So when we look at these interactions, really these are interactions with carbon, hydrogen, and oxygen. It's by number much more likely to interact with hydrogen and very likely to interact with oxygen because we're mostly water, and so you mostly have H2O floating around there. But carbon is the other big thing that we interact with. There's other metals too, or there's other things too, such as metals. Okay, think copper, think iron, think magnesium. Right? Some people take magnesium supplements, right? And there's other different things, trace elements, let's say. But for mostly carbon, hydrogen, and oxygen. In fact, the sugar that you eat, right, and all the proteins that you build are all built on those things, okay? Nitrogen as well. We breathe 78% nitrogen in the air around us. So all of those elements floating around in our body are what comprise our body are what the X-ray beam is going to interact with. Now, luckily, we don't have to learn the different interactions for each different atom, for each different type of atom. We just have to say that the X-ray beam interacts with these different types of atoms. Okay. So remember, the X-ray beam can either be completely transmitted without interacting with anything. That's pretty rare, okay? Or it has some interaction with a tissue atom, with an atom in the body's tissue. So the first type we're going to talk about is called the photoelectric interaction. The photoelectric interaction is pretty neat because it was discovered in 1905. You guys know somebody named Albert Einstein, right? What's he known for? Oh, that's so bad, so embarrassing. Oh man, I feel so bad. Poor Einstein. E equals mc squared, right? Equating energy to mass, right? He is most well known for his theory of gravity, general relativity, the bending and warping of space-time. But he won a Nobel Prize in science and in physics. He didn't win his Nobel Prize for the theory of relativity, general or special relativity, which equals mc squared, or gravity. Didn't win a Nobel Prize for that. Didn't win a Nobel Prize for a lot of other things. He won a Nobel Prize for discovering that atoms, when exposed to certain types of energy, certain types of light, can emit electrons. Electrons can fly off of them. It's called the photoelectric effect. Okay, he demonstrated it and he wrote a paper on it, and it was actually one of the first real true insights into what atoms were made of. Okay, it was like the same year that Ernst Rutherford did his experiment to determine that atoms had a nucleus. Okay, we didn't know that atoms had a nucleus before these years. So this is real early on, right? Beginnings of what you would think of as quantum mechanics. By the way, this is a little tiny snippet, tiny nugget of quantum mechanics. Okay, tiny nugget of it. The photoelectric effect. Okay, so what a photoelectric effect is. A photoelectron is an electron that has absorbed a photon. Photoelectron, okay? A photoelectron has absorbed a photon. So here's the thing about electrons. Electrons are electrically charged particles that interact with the electric and magnetic field. Or said it another way, they interact with the electromagnetic field. Well, what is a vibration in the electromagnetic field? It's a photon. Okay, so electrons interact with the electromagnetic field by absorbing or emitting photons. Okay, an electron with too much energy can emit a photon to lose energy. You know that as characteristic radiation. An electron with lower energy can absorb a photon and increase its energy. Okay, either jump up a couple. You notice how the atoms have the electrons arranged into shells. An electron, if it absorbs enough energy, can jump up a shell level. If it absorbs a significant amount of energy, enough to get out of the atom, it can jump right out of the atom and go speeding away. When an electron is given enough energy to where it can speed away from an atom, we call that a photoelectron. Okay, so importantly, electrons can absorb or emit photons. Okay, that's where X-rays come from, right? X-rays come from fast-moving electrons slowing down, right? That's Brem's radiation in the X-ray tube. Hopefully this is all starting to make a little more sense as we do more and more and more of this. So the photoelectric effect is when a photon is completely absorbed by an orbiting electron. Incoming photon, where'd this photon come from? The X-ray tube, right? Came down from the X-ray tube. This photon is part of the primary beam, right? And now it's interacting with the patient's tissue atoms. This tissue atom happened to just be in the right spot for this photon to strike an inner shell electron. And it happened to have enough energy to kick that electron out of the atom, okay? So here's what it is. No secondary or scattered X-rays are left over. Where did the X-ray go? Yeah, it's been absorbed by the photoelectron, right? Or it's been absorbed by the electron, which now is going to be called a photoelectron. This only occurs in the innermost electron shells in atoms, and I'll give you a reason why later, but roughly speaking, it's because the inner shells are held tightly in place, and it takes a lot of energy to eject them. So a photon's likely to give up all of its energy doing this. If this happens with an outer shell and a valence electron on the outside, it's more likely that the electron will be flicked away, kicked out, and there will be still a leftover photon, okay? Which is an interaction we'll talk about in a minute here. This type leaves no X-ray photon left. It's gone, okay? The X-ray photon is absorbed by the electron, giving the electron increased kinetic energy. Notice how it can work backwards, right? A fast-moving electron can slow down and emit a photon, or a slow-moving electron can speed up by absorbing a photon. This works both ways. I think of photons, and usually for analogy purposes, as the monetary exchange, right? That's the way electrons exchange money, basically, right? Exchange value. Yeah, they can only exchange, or they can only give or gain photons of energy, photons of electromagnetism. Increased kinetic energy of the electron causes the electron to be ejected from the atom that it's in. A photoelectron is an electron that has captured, or the better word that I like to think of is absorbed, right? Converted the kinetic energy of the photon into the kinetic energy of the electron. Now it's a photoelectron. Two important things are true here. The atom has lost an electron. So if this atom was neutrally charged and loses a negatively charged particle, what overall charge does the atom have now? It has no charge, and now it loses a negative charge. It has a positive charge now, right? That atom is said to be ionized. Why is that bad? It's bad. Why is it bad? Yeah, you're on the right track. What are you made of? Atoms of carbon, hydrogen, oxygen, right? Meaning your DNA is also made of these things, right? And atoms bond together by their electron interactions. Okay, so if you take away an electron from an atom, and that electron was being used in a way to be bonded to another atom, let's say it's on a strand of DNA, right? You might break the strand of DNA. Okay, if you break the strand of DNA, you cause a DNA mutation. Your body can fix most of DNA mutations, but not all of them. And if this happens over longer periods of time, you get more and more DNA mutations, right? This is the reason X-rays are harmful, is because X-rays can ionize atoms and break chemical bonds. It can turn water, through a series of interactions, can turn water into hydrogen peroxide. You know, hydrogen peroxide is toxic to cells, right? X-rays can turn water into hydrogen peroxide in your body's cells. In fact, that's the most likely interaction to happen because you're mostly water, okay? When you do that, the hydrogen peroxide can damage the DNA. So even if you don't directly strike the DNA, ionizing the water around the DNA creates charged particles. Now, here's the other problem. You have created an ionized atom, and you have a second charged particle just shooting around inside near other atoms, right? So this photoelectron can now go and bump into another electron and knock another electron out, maybe, right? If it has enough kinetic energy. That's similar to the Brem's interactions or characteristic interactions in the X-ray tube. So this photoelectron is dangerous, and so is the ionized atom. Okay? These are called ion pairs when this happens. We've created an ion pair. The second most important part of this is this photoelectron cannot reach the image receptor. Okay? That means that the spot where this happens in the body leaves a microscopic spot where no X-rays are going to hit the receptor. This accounts for the white on your images. This is where the white comes from on X-rays, the bones and things like that. Your subject contrast, the grayscale that you get to see, is primarily this photoelectric effect is what is primarily responsible for giving you that. So let's read what's down here. The photoelectric effect is primarily responsible for the production of subject contrast in the latent image carried by the remnant beam, and we couldn't make X-rays if this didn't happen. Okay, so the fact that this happens is important to make X-rays, but we also have to keep in mind that using X-rays is potentially harmful to the body. Now we have an entire module where we get to talk about how harmful X-rays are, and right now it's easy to think X-rays are very harmful, and they're not harmful. But in the radiation safety module, I'm going to give you guys a little bit of a more nuanced understanding of it, and you'll get to see like it's not as bad as we necessarily make it sound. But X-ray imaging would be impossible without the photoelectric interaction. So what do you got? What needs to happen here, right? Well, one thing. Sorry, my mouse is being funky. Okay, fine. Let's click that then. One, the incoming photon needs to have slightly more energy than the binding energy holding the electron in place. Slightly more energy. That is to say, the binding energy is listed in kV, or keV to be more specific, kilo electron volts. You guys know what it is for tungsten, right? You know the K shell of tungsten is bound with 69.5 keV of energy, but carbon, hydrogen, oxygen have lower binding energies. But let's just use an imaginary number, okay? Let's say this inner shell electron was bound with 40 keV, okay? So that electron is being held in place. Okay, and that electron would need to absorb at least 40 keV of energy in order to leave its position. Okay, that means the incoming photon has to have 40 keV worth of energy or more, right? If it has a lot more, like 80 keV worth of energy, then it's more likely that the photon coming in would eject the electron and still keep going on its merry way. Okay, as a new photon, which is an interaction we'll get to talk about in a moment. But if the energy of this photon is like 41 or 42, something just a little bit higher than the binding energy for the orbiting electron, you will deposit all of the photon's energy into the electron, not just some of it. Okay, and when you do that, you eject the electron, and you have completely lost the photon. Okay, so if this incoming photon had 42 keV worth of energy, and it took 40 keV worth of energy to eject the electron, what happens to the other 2 keV if there's no more photon left over? It took 40 to remove the electron, but there's no photon left over. So you have to account for the other 2. There's no such thing as a loss of energy. Yeah, it goes into the kinetic energy of the electron. That extra 2 keV sped the electron up. Okay, and again, this only happens if the incoming photon has slightly more energy than the binding energy holding the electron in place. Okay, if it has a lot more energy, the interaction is likely to be a different type. Okay, which we will talk about in a moment. Okay. There it goes. Okay, so let's take a brief look at the binding energies for important elements. And okay, so show of hands, don't be shy. Who has no idea what K shell, L shell, M shell mean? You can raise your hand, don't be shy. Fantastic, great. This refers to which shell level your electrons are in. Okay, electrons are arranged into shells. Okay, let's go back to this image. Electrons are arranged into shells. The closer, see this, so there's one shell there and another shell here. Okay, and there's a formula to calculate how many electrons can fit in each shell. We don't need to worry about that. But what's important right now is the electrons are arranged into shells. Just like me being here on the ground versus me standing up on top of the table, right? I'm more tightly bound to Earth when I'm standing on the ground, right? And when you put me on top of the table, I have less gravitational pull. There's less gravity pulling me to Earth because I'm further away from Earth, right? Now it's a teeny, tiny bit less, but it's less, okay? And extrapolate it all the way out. I stand on the table, I have a little bit less energy binding me to Earth. I hop on an airplane, I have a little bit less energy binding me to Earth. And then you put me on the International Space Station orbiting Earth, and I have a lot less energy binding me to Earth. I can actually orbit around the Earth and not fall down to the ground, right? That's analogous to binding energy. The closer the electron shell is to the nucleus of an atom, the more tightly held in place it is. Okay? It's easier to remove electrons from this shell than it is to remove them from this shell. Okay? The shells are given names. The innermost shell of an atom is called the K shell, for no good reason, just because. Okay? We could have named it the number 1 shell. In fact, we do sometimes call it the first shell, or the 1 shell, shell number 1. The L shell is second, and it just goes in alphabetical order. K, L, M, N, O, and P. Okay? And the further away an electron is, the further out it is in its orbital shell, the less energy there is holding it in place. Notice for carbon, and also notice that carbon has K shell and L shell, but no M shell. This is a more complicated question, but why, than maybe you're prepared for, but why is there no third shell of electrons in carbon?
Because they already filled up in the L shell.
Yeah, there's no electrons to fit in the M shell, right? How, Parrish, where's carbon at on the periodic table? It's C, capital C. 6. Okay, it's number 6 on the periodic table. That means it has 6 electrons. A neutral carbon atom has 6 electrons. Okay, 2 fit in the inner shell, and the other 4 filled up the second shell. Okay, there is no need for a third shell. Okay, but dense metals like tungsten, or lead, or barium, they need to use the other shells because they have so many electrons because they're so big. Okay, carbon, -2, let's say we'll just say -2. -2 keV holds it in place in the K shell. -0.02 keV holds the L shell electrons in place. There is less energy holding these in place than there is these. Okay, these are the closer ones, the K shell, and these are further away. So if an X-ray photon is going to interact with carbon's K shell and eject the K shell electron, how much energy does the photon have to carry? All you need to know is that if you want to eject the K shell, that incoming photon has to have more than that, okay? That much or more, okay? So, and what's cool about the photons is photons have no electric charge, so the negative means nothing to a photon, okay? If you're a photon and you have anything above 0.284 kV of energy, you can eject carbon's inner shell electrons if you happen to interact with it. Oxygen, which is much more likely to interact with oxygen, if an X-ray photon has more than 0.543 keV, so if it has 0.6 keV worth of energy, an X-ray photon can eject the K shell in oxygen. Now look down here. Look at tungsten. It takes 69 keV at least to eject the K shell electrons in tungsten. They're held tighter in place because tungsten's nucleus is so much bigger. Okay, lead is even heavier. Okay, so we know what the binding energies are for the common atoms in the body: carbon, oxygen, calcium, iodine, barium, tungsten, and lead. We know all of these. Notice we didn't list hydrogen, okay, but it's there. By number, it's actually in the highest quantity. It's just so light that it doesn't matter. It's so easy to ionize hydrogen. But we know these, and so we can say that if a photon has that much or a little bit more, it can eject electrons and cause the photoelectric effect to happen. Okay, so the next effect is similar. The next effect is similar, but the main difference is it's more likely to happen in an outer shell than an inner shell, and you get a leftover secondary photon from it, okay? Because in photoelectric interactions, there's no leftover photon, nothing to expose the image, okay? Compton interactions, okay, the person's name was Compton, okay? Compton interactions give you a leftover photon. Now, I think these are easier to understand, okay? So it's partial absorption of the X-ray photon's energy. By the way, this is not all being shown to you for no reason. These are going to be test questions on the state exam. The state board will ask you about Compton interactions, when they're likely to happen, photoelectric interactions, and all of these. They might show you diagrams, they might just ask you questions, but this is part of being an X-ray tech, is understanding how X-rays interact with the body, so it's not for nothing. Okay, partial absorption of the X-ray photon's energy. Secondary radiation is emitted, and it's usually scattered, meaning that it usually travels in a different direction than the original photon was traveling. So if you got a photon coming down this way from the X-ray tube, has a Compton interaction, it can go in any random other direction. Now here's the key to it. The higher the energy for the photon, the more likely it is that the secondary photon is going to keep traveling downward, okay? The lower the energy of the original primary photon, the more likely it is it's going to scatter in some random faraway direction, okay? Good. Secondary radiation is emitted. We call this photon coming out secondary radiation because it's a different energy. It's a different photon. It's not the same photon. This 80 keV photon interacts with an outer shell electron. The name for the outermost shell of atoms, the outermost shell of electrons in atoms, is called the valence shell. Okay, you probably remember in science class covalent interactions or covalent bonds, right? Useless to us in high school, but all of a sudden in X-ray physics it becomes important, right? So covalent bonds are bonds between the valence electrons. The outer shell is called the valence shell. Electrons in the outer shell, well, maybe you can tell me, are they held in place with more or less binding energy than the inner shell? Less binding energy, right? So it's easier to remove them than it is to remove the inner shell ones. So in this example, an 80 keV photon comes in, ejects an electron, and leaves with 78 keV. How much binding energy was there? 2, right? Because we started with 80 and we left with 78, so we lost 2. Just remember this, there is no such thing as a loss of energy. The rule says energy is conserved, okay, because we said so. And it's what all experiments seem to show, okay, energy is conserved. So we started with 80, left with 78, we could measure that, and we lost an electron. So we have to say that the electron it could have had 1 keV of binding energy, and the rest went into making the electron fast, kinetic energy of the electron. Okay, so we don't know how much binding, from just looking at this, we don't know how much binding energy there was, but we do know that there was enough energy lost to eject the electron, make it move fast and away from the atom. It's ionize the atom and the electron's moving fast, and we know we lost 2 keV. Okay, good. So we call that thing, the electron, we call it a recoil electron. It's ejected from the atom because it absorbed, this is what's cool, right? In the photoelectric interaction, the electron absorbed all of the photon's energy. In this interaction, the electron absorbed only a small amount of the photon's energy, and that was enough to get it out of the atom, to ionize the atom. The recoil electron cannot reach the image receptor. This guy down here cannot reach the receptor. What's it going to do? It's going to go run into another atom and maybe knock out an electron from another atom, maybe make a characteristic interaction or a Brem's interaction and make some other scattered photons, maybe, okay? But it's definitely not going to get to the image receptor. But the scattered X-ray photon can. As the energy increases, as X-ray photon energy increases, the beam energy increases, Compton interactions are likely to decrease in their likelihood. Okay. And importantly, the incoming photon has to have way more energy than the binding energy for the electron it interacts with. What would happen if it didn't have? What would happen if the incoming photon had less energy than the binding energy of the orbiting electron? Would it eject the electron?
No, wouldn't it just stop because it hit a wall?
So it wouldn't have hit a wall, because remember, electrons can absorb photons. So the electron would absorb the photon. The electron would momentarily increase in energy. This is the next interaction, by the way. Would momentarily increase in energy. The electron would jump up a shell level, an imaginary shell level, and then it would jump back down. When the electron jumps back down, it re-emits the photon as a new photon. I'll show you that in a moment here. So Compton interactions have to have a lot more energy than the binding energy. Photoelectric interactions have to have slightly more photon energy than the binding energy for the electrons. And the next one, well, I'll talk about the next one in just a moment here, because you need to know the other names for Compton. Compton scattering is also referred to as modified scatter or incoherent scatter, because we wanted to make it difficult for you. We wanted to make it hard for X-ray techs to take tests. No, I'm just kidding. It's because different scientists learn different things at different times, and people all over the world got to name things. Okay, so we have different names for things. So modified scatter. We call it modified or incoherent scatter because the energy of the scattered photon is different, and you can't predict exactly where the photon is going to go, where it's going to scatter. That's why it's scatter. The scattered photon, remind yourself, is considered to be a new photon because it has a different energy than the original incoming incident photon. X-rays are identified by their binding, by their energy. Sorry, I thought it said binding energy. I thought that was wrong. X-rays are identified by their energy, wavelength, frequency. That's what identifies an X-ray or any electromagnetic radiation. Wavelength. Okay. So don't you worry, we don't got to worry about the formulas for this. We just have to say that we have more significantly more energy than the binding energy. You'll have an interaction with an orbiting electron, usually outer shell, ejects the electron, ionizes the atom, you have a scattered photon left over. Now, it is possible for a single X-ray photon, a series of Compton interactions can occur until the remaining energy is slightly above the binding energy, and then a photoelectric interaction happens. Okay, so follow this through from right to left. You have a high energy photon coming in. It happens to have enough energy to eject an orbiting electron. So here you have your orbiting electron ejected. Okay, the scattered secondary photon goes on its way, finds a new atom to interact with because there's lots of atoms, and it has tons of energy left over, right? It does it again, ejects an electron, you have another photoelectron, and now there's less energy in the X-ray photon, but it has enough energy to go do this again, okay? It ejects an electron, and now it has lost so much energy that the next time it interacts with an electron, that electron's just going to absorb the entirety of what's left over in that photon. And the photon now goes and dumps all its energy into an electron, becomes a photoelectron, and you have no leftover Compton scatter. Okay, so it is possible for Compton scatter to finish as a photoelectric interaction and never reach the image receptor. Okay, so Compton scatter can cascade and turn into photoelectric interactions in the body. Some of them do, some of them don't. And as you get higher and higher in energies, it's more likely that the photon will make it all the way to the receptor and won't Compton its way down to a photoelectric interaction. And here's sort of why. Scattered X-rays with higher energies are deflected less from the direction of the original X-ray. So they travel in a more forward direction and are likely to reach the image receptor. So here you have 100% energy interacts with an atom, and then it shows you the percentage likelihoods of scattering at different directions. Okay, which then brings us to backscatter. Backscatter is exactly what it sounds like. It's scatter traveling back the opposite direction from the patient. In diagnostic radiography, most of the scattered radiation having lower energies from 2/3 to 3/4 of the original X-rays, scatter at reversed oblique angles to the central ray. This is called backscatter. This is scatter. The X-ray beam interacts with the patient, and scatter can travel in all directions around the room, not just towards the image receptor. Some of the scattered X-rays reach the image receptor, and those are sufficient to degrade the image. Scatter is random, and it sort of creates a fog on the image. This fog reduces image contrast and makes the visibility of structures more difficult. And at higher KVs, the scatter generated is always higher. Excuse me. At higher KVs, the scatter that's generated is more energetic, and because it has more energy, is more likely to head straight towards the image receptor. So at higher KVs, you get more scatter, and you get more of that scatter reaching the image receptor and fogging the image. So at high KVs, scatter on the image, fog on the image receptors is more common. And that's why at high KVs we tend to use the Bucky trays or the table or wall Buckies, and it's simply because they're going to absorb that scatter radiation more effectively. You will not see us doing tabletop exams at like 80 and 90 kV. Okay, when we do tabletop exams, we do things like 50 and 60 and 70 kV, low energy, because we make more scatter as we get to higher energies. So chest X-ray is almost never going to be taken without a grid. Okay. All right. So good. So at this point, we've described photoelectric interactions, complete absorption of an X-ray photon, no leftover photon, ionized atom, white spot on the image. Then we described the Compton interaction, modified or incoherent scatter, scattered X-ray photon, reaches the image receptor, ionizes an atom, but still scattered photon importantly reaches the image receptor. The next is a little bit different. Those first two caused ionization of an atom. This next one doesn't. This is called coherent scatter. So, yep, you got to remember what's incoherent scatter and coherent scatter. Okay, the coherent scattering is momentary absorption of a photon followed by immediate re-emission of that same energy photon. It's still going to be a new photon though. Okay, I'll tell you why in a second here. Oh, let me just give it to you. Remember, photons are characterized by their energy and the direction they travel. Recall that X-rays only travel in straight lines. Okay, so an X-ray photon going this way and one going that way are different photons. Okay, X-rays only travel in straight lines. Secondary radiation is emitted, which is usually scattered in its original direction, from the original. The atom does not become ionized. Here's why. The energy of the incoming X-ray photon is less than the binding energy. So if the binding energy is 10 keV, okay, the photon has less than 10 keV. Maybe it has 9 or 9.99999, still not enough to eject the electron. So the electron can absorb the photon. What happens when an electron absorbs a photon is it tends to jump up shell levels in the atom. So if whatever shell it's at jumps up a shell. And then pretty much immediately after that, the electron and the rest of the atom are going to try to get back to equilibrium, get back to neutral, right? And the way an atom gets back to neutral is it emits photons, okay? And remember, conservation of energy. So if it absorbed a photon with 9.999 keV of energy and didn't eject the electron falls back down into its original position and re-emits a photon with that exact amount of energy. Okay. The orbiting electron is raised to a state of excitation. The atom is not ionized, the atom is excited. This is the principle behind glow-in-the-dark stuff. Okay, glow-in-the-dark things, you hold them up to light, right? The electrons of the glow-in-the-dark material absorb photons of light, they get excited, and then because of the special design of the material, they don't all jump back at one time. They all start to jump back into their original positions and start firing off photons of like greenish light. Okay, that's why you see most glow-in-the-dark things are green, right? So they're firing off photons in that wavelength to where you will see green. Re-emits the X-ray photon. The X-ray photon re-emitted is identical in energy, but it's scattered in a different direction. And as I said, X-rays travel in straight lines, so it's a new photon. The scattered photon can now reach the image receptor and degrade contrast. Now, if the scattered photon went the exact same direction as the original photon, perfect. It's a great representation of the body, okay? But the scattered photon is going to go a different direction and hit the image receptor over here, where the anatomy is over here. It's not going to represent anatomy, okay? We want, in order to carry a coherent signal, we want the photons traveling through the body and becoming part of the remnant beam to carry information about the patient, right? And if they're all traveling in random directions, they don't carry any information about the patient. Scatter carries no useful information. Scatter only degrades the image because it starts here, ends over here, and is not giving you any image of the body part. It's just hitting the image receptor and causing fog on the receptor. Coherent scatter goes by two names, coherent scatter or unmodified scatter. Why might it be called unmodified? What is the thing that's not being modified? The new photon, right? The new photon is the same as the old photon. Why? Because the atom had to get rid of all of its energy, all that excess energy, so it re-emits the photon. Now, there's two sort of schools of thought behind this, and it doesn't matter which one you think of because they both are the same thing, but we call them Thompson and Rayleigh scatter. They're both coherent scatter. They are both this, okay? But you can think about it as if one orbiting electron absorbed the photon and then re-emitted it, or you can picture it as the atom as a whole absorbs the photon and re-emits the photon. It doesn't matter which one you think about, okay? But just remember that coherent or unmodified scatter is referred to as Thompson or Rayleigh interactions, and they're both very similar. It's just the way you think of them. Okay. Those are our three main interactions. Lastly, following any ionizing event in the body, you may have a characteristic interaction. Because recall that if we eject an electron and it's an inner shell electron like in the photoelectric interaction, the outer shells are going to fall down into these inner shells and you're going to get what's called a characteristic photon emitted. So this is after the atom has been interacted with. Scattered photons are already on their way. Photoelectrons are already on their way away from the atom. Now the atom is left behind, ionized, and trying to regain equilibrium. Okay, and the way atoms regain equilibrium is by taking electrons from the outer shells and filling the inner shells up. Eventually, the outer shells are going to be left with vacancies, and they just get filled, interacting with other atoms, molecules changing shape, and so forth. But characteristic radiation can follow any ionizing event in the body. Remember, characteristic radiation was one of the interactions that happens in the X-ray tube, right? This also happens inside of the body after any atom is ionized. Importantly, so this top thing says basically what I said, but importantly, the photons created by characteristic interactions are too low in energy to reach the image receptor. They're usually ultraviolet light, so they're lower energy than X-rays. Some of them could even be visible light. You light up a little bit, right? Tiny bit. Okay. All right. We have the last topic that I'm going to get to today, okay, which is two topics: attenuation and subject contrast. So now that you've learned the three main interactions that happen in the body, photoelectric, Compton, and coherent scatter, do not take them for granted. You need to know them, okay? So you're going to need to look back on these and review.